One approach that you can take to using simulation is to use a coin flipping applet. There's another approach that you can take as well, but I just want to formalize this method for testing hypotheses regarding a proportion using simulation. First and foremost, you need to verify the variable of interest in the study is qualitative with two possible outcomes. For our situation, you either pass the class or you do not. You then structure your null and alternative hypotheses. You then build a null model that generates data randomly under the assumption the statement in the null is true. So in our last example, we built our null model using a coin where the coin was fair because you had a 50% chance of getting a head, meaning you pass. You had a 50% chance of getting a tail, meaning you did not pass. And then you use that null model to estimate the p-value. And then finally state your conclusion. So we did all that with a coin. Now let's do it using the Urn Applet. So here's the scenario. In a Pew Research poll conducted in 2017, it was reported that 43% of adult Americans, so we're going to define adult American as aged 18 or older, believe the reason a person is rich is because the individual, quote unquote, had advantages in life. In a random sample of 80 Republicans, it was found that 23 believe the reason a person is rich is because the individual had advantages in life. Does the sample evidence suggest a lower proportion of Republicans believe the reason a person is rich is because the individual had advantages in life? So there's your question. Here, our statement of no change, no effect, no difference would mean the proportion of all adult Americans who believe a person is rich is because they had advantages in life is the same as the proportion of Republicans. No difference between the two groups. If there's no difference between the two groups, that would suggest that the null is that the proportion is what value?
It's no change, so it'd be 0.43 or 0.43.
Correct. The statement of no change or no difference is 0.43. There's no difference between all adults and Republicans in how they feel. And then we're going to compare that to what we're trying to show. And we're trying to show, does the sample evidence suggest a lower proportion of Republicans believe a person is rich because they had advantage in life? So what does that mean we're trying to show?
That it would be P and then is less than.
Yep, P is less than 0.43 because we're trying to show the proportion is lower among Republicans. Okay, so that's what that's our research goal. Now what we're going to have to do is test this using simulation. We're going to see how likely it is to observe results such as 23 out of 80 or fewer saying a person is rich because they had advantages in life under the assumption the true proportion is 0.43. We could, just so you know, we could use a coin to do this. However, we would have to weight the coin. So you would say, I'm going to build the coin applet where the likelihood of getting a head is 0.43, and then the likelihood of getting a tail is then therefore 0.57. And then if you flip the coin and get a head, that means you found a Republican who believes a person is rich because they had advantages in life. And if you get a tail, they did not believe that. So that's one approach you could take. The problem is that unfair coins don't have intuitive appeal. And so instead of using the coin, we're going to use what's called the Urn Applet. The Urn Applet literally allows us to build out this population under the assumption the statement in the null is true. So that's laid out for you right here. So I'm going to read this to you. We're going to assume, so that we can build the population, there are 80 million registered Republicans in the country, which is about right now. that when we build the urn, we're going to make 43% of them green balls. So we're going to build this urn applet so there are 34,400,000 green balls. Each of those green balls is going to represent a Republican who believes the person is rich because they had advantages in life. And then the remaining balls, 45,600,000, are going to be red. They do not believe a person is rich because they had advantages in life. So note, super important here, we're building the model, the null model, under the assumption the statement in the null is true, that 43% of them Republicans believe a person is rich because the individual had advantages in life. So the Republicans are no different than all adult Americans. So we're going to go applets, simulation, urn sampling. I have green balls and I have the red ones. I want the urn applet to have 34,400,000 green balls. Those are the Republicans that believe a person is rich because they had advantages in life. And then 45,600,000 red balls. Those are the Republicans who do not believe that a person is rich because they had advantages in life. Remember, our original survey surveyed 80 Republicans, and therefore we're going to draw 80 balls out of the urn. And also remember that out of the 80 in our original survey, 23 believe the person is rich because they had advantages in life. And so we're going to set this up so that the number is less than or equal to 23. Why? Because we want to know if a lower proportion of Republicans believe a person is rich because they had advantages in life. And we observed 23 out of the 80 that said, I believe a person is rich because they had advantages in life. The p-value is the likelihood of getting a result as extreme or more extreme than that observed. Here, because it's a left-tailed test, anything 20 that we observed that is 23 or fewer would be as extreme or more extreme. Click compute. Let me do this one time so that you can see what the process is. But first and foremost, we built a population of 80 million Republicans and designated them either green or red. Any ball that is green is a Republican who says, I believe people are rich because they had advantages in life. Any ball that is red is a Republican who says, I don't believe that. The model was also built out assuming 43% of Republicans believe people are rich because they had advantages in life, because that was the statement in the null hypothesis. In other words, 43% of my balls are green, 57% of my balls are red. So I go in and I'm going to randomly sample 80 balls and record the color. The color of the ball is simply their response to the question. So this first ball here, red, that person said, no, I don't believe the person is rich because they had advantages in life. This green ball says, the person said, yeah, I believe a person's rich because they had advantages in life, so on and so forth. So in my survey of 80 Republicans, 32 said, I believe people are rich because they had advantages in life. Now that's me doing that survey once. If I do it a second time, this time I got 37 saying, I believe a person is rich because they had advantages in life. I'm going to do this over and over and over again to see how often I observe results as extreme or more extreme than those I actually observed. There we have it. So notice the proportion of times we observed 23 or fewer out of 80 saying, yeah, I believe a person is rich because they've had advantages in life, is 0.0068. So I'm just going to explain this in terms of the urn, and then we'll explain it in terms of the context of the hypothesis test. We surveyed 8 Republicans. How many times? 5,002 times. And observed 23 or fewer who believed the person is rich because they had advantages in life in only 34 of the surveys. This results in a p-value of 0.0068, which is about 0.007. So if 43% of Republicans believe, whoops, I spelled that wrong, believe a person is rich because they had advantages in life, we would observe 23 or fewer out of 80 saying a person is rich because they had advantages in life, and about 7 of every 1,000 repetitions of the study. In other words, we just observed something incredibly unusual if 43% of Republicans believe people are rich because they had advantages in life. Right? And so we would take that one instance, that sample evidence of 23 or fewer, and say, wow, this really is not consistent with 43% of Republicans believing that. So I think the better explanation is fewer than 43% of Republicans believe that. So again, this is a p-value. So a p-value is a measure of likelihood of observing results as extreme or more extreme than those actually observed under the assumption the statement in the null is true. The lower the p-value is, the stronger the evidence against the statement in the null.
Now, is that intuitive, or is there a number you compare it to?
That is a phenomenal question. Are there hard and fast rules for what the cutoff is? So I'm going to give you a very, very long answer to that question in a second. Okay, so we'll hold that question for a sec. This is how we use hypothesis testing using the p-value approach, and then I want to elaborate a little bit more on this. If the probability of getting a sample statistic as extreme or more extreme than that actually observed is small, under the assumption the statement in the null is true, we're going to reject the statement in the null hypothesis. But the p-value approach recently has received a lot of media attention because the p-value is the method by which all journal articles publish results. And so it turns out that oftentimes the p-value that one study gets is going to be different than the p-value a second study gets. And that should feel logical, right? Like here I got a p-value of 0.0068, right?
Right.
Let me redo this. Let me just reset this applet and do this 5,000 times. This time I got a p-value of 0.0072. Notice that the p-value is different for this second simulation, but they're fairly close.
Mm-hmm.
P-values are going to vary from study to study because you have different individuals that you survey, right?
Right.
And so the question becomes, hey, if I do this study and I get a small p-value, are you going to be able to do the same study and get a similarly small p-value? If you are, you are able to do what's called replicate my results. If you weren't, you would not be able to replicate my results. And so that becomes the crux under which ultimately you decide, yes, this was statistically significant. Can other people replicate the results that I get? That's sort of an aside. What you'll see in the textbook is I lay out for you p-values and what they actually suggest. In other words, p-values in and of themselves have different levels to them. The bottom line is the smaller the p-value is, the stronger the evidence against the statement and the null. But in textbook circumstances, we have to have some sort of criterion under which we judge, am I going to reject or not? And that's where we use this rule of thumb that says if the p-value is less than 0.05, and that would be your level of significance, alpha, we reject the statement and the null hypothesis. The bottom line is I'm going to be giving you alphas in the homework, and it's basically your rule is going to be if the p-value is less than the level of significance alpha, you reject the statement and the null. What I often say is if the p is low, the null must go. Okay, that helps you to remember. If the p is low, the null must go. But a p-value of 0.02 does not show as much statistical significance as a p-value of, say, 0.001. Because a p-value of 0.02 means if the statement in the null is true, you'd see these results about 2 times out of 100. If the p-value is 0.001, that means if the null is true, you'd see this about 1 time out of 1,000.
Jeez.
Right? And so that's why it's super important that you know how to interpret the p-value from a relative frequency point of view like we did here. A p-value of 0.007 means about 7 times out of 1,000.